So we put all of these three together and did, again, the same thing of discussing what are the pluses and minuses, what are the error ranges, and we had a statistician from NIST with us, and he put together our numbers plus our uncertainties, and we came up with a range of 35 to 60,000 barrels per day. Now, and that's using video evidence, using sonar. Woods Hole had a sonar team, and they acoustically profiled the jet, and using these pressure measurements. So now it's three separate pieces of information. So this number is probably the number that's going to stick around for a while. You know, it's been hard to keep track of the numbers lately, but this number, I think, is going to be the one that we refer to unless something major happens. Like if there's a catastrophe with the well, and their well could be because it's compromised. So you know, we're everybody who knows what's going on in the inside of this is keeping their fingers crossed that nothing major changes until the relief wells are drilled in August. All right, so I thought I'd say a few words about impact. I'm not an environmentalist, and everybody, you know, all the shows that I've interviewed with have asked me, you know, what's the impact of this flow rate? You know, flow rate times time tells you the total amount of the emission. What's the impact of this oil in the environment? You know, I don't have any idea. What I know is that if the flow is let's say at the low end, 35,000 barrels a day, that's 7 times more oil in the environment than BP was admitting to. So I did some calculations because everyone likes to put this disaster in terms of Exxon Valdez's, which was prior to this our worst oil spill in the U.S. So this works out to 1 Exxon Valdez every 4 to 7 days. You know, so let's say best case, that's 1 Exxon Valdez a week that's being poured into the Gulf of Mexico. And then I thought I'd calculate the total amount of the flow. So if the relief wells are completed on schedule in the middle of August, that's 17 to 30 times, or 17 to 30 Exxon Valdez's over the course of this accident. And I put this little picture up here, this thing that looks like a sausage is an eel that's swimming into the oil. They seem to like it for some reason. I don't know if they swim out again, so I'm not sure if this eel is a goner or if it holds its breath when it goes through. Anyhow, to finish up, I thought I'd show you these working groups. So this is the flow rate technical group when we met on June 13th, so just last Sunday. There's me, there's Marcia McNutt, she's the one you've seen in the giving the press releases for the group, and I won't name everybody else. Then the day after, in Secretary Chu's conference room, this is Secretary Chu right there, this is Secretary Salazar, they were both leading the discussion, and then I'm not in it because I was taking a break and thought I'd catch a picture while I had a chance, so. Anyhow, with that, I'll conclude, and I'd be happy to take any questions. I'm not sure how we're going to officiate this. Do we? I think we decided there isn't a microphone, right?
There's not another microphone.
All right. So let's go over here.
So this may be a naive question, but presumably there isn't an infinite amount of oil under the ground. Has anybody thought about seeing if the flow rate changes over time?
Yeah.
As the pressure drops when more oil is leaked?
Right. So the question is, what are the dynamics of this thing as time passes? Does the well blow down? And essentially, this is like a balloon. If you blow up a balloon and you don't seal the end and you let go of it, it flies around the room, and then eventually it stops flying around the room. It's exactly the same thing. So what we have is a pocket of oil that's under 10,000 feet of rock and 5,000 feet of water. And that's all pushing down on it. That's what creates the pressure in the oil well. And what we do, or what the petroleum companies do, is they drill a hole into that reservoir. And now this 15,000 feet of stuff that's above it being pulled down by gravity squeezes that reservoir and causes it to shoot oil out. And eventually, there won't be any more oil. So, so certainly the flow rate is expected to change with time, and eventually it would run out on its own. There's one data point that I can point out, which is in 1979, there was a blowout in Mexican waters, and it was called Ictapa, and that one ran for 10 months before they could seal it up. So I'm not familiar with the case. I don't know if efforts to seal it failed or if they just decided it was too hard. Let's come over here.
So is your PIV based on the entire surface of the flow or just the oil? Are you calculating the total amount of material ejected or just the oil? And is the dynamic, are the turbulent structures that you're measuring different on the methane side versus the oil side?
Yeah, so the question is, what is the PIV, what structures does the PIV identify? So what everybody in the group did was we identified time periods of the movie when the flow was entirely oil, and then we try to measure as close to the exit of the pipe as possible. Because what happens to this jet, as it comes out of the pipe, the seawater pulls on it, tries to slow it down. That causes the jet to broaden, and it's got these turbulent structures, and what they do is they start pulling water into the jet, start mixing with water. Now, oil and water don't mix, so the dynamics of the jet are a little bit different than, than any jet you'd be familiar with. But basically, as long as we measure close to the exit of the pipe, that doesn't matter so much. So we try to measure the time when the flow is just oil, and then we use a property called the gas-to-oil ratio, which is a property of the oil in the reservoir. And that happens to have a certain ratio, a certain fraction of what comes out of the pipe is gas, and some fraction is gas, some fraction is oil. So that's the short answer. Yeah, there's one right here.
Describe a little bit about the laboratory apparatus you used for your initial work.
Yeah, so what's the laboratory apparatus? In fact, in probably 90% of the talks I've given prior to this, I would have that in there, but I thought a schematic at a bar might go unappreciated. But basically, when we do this in the lab, it's actually not a whole lot different than the equipment that was available here. So really, all you need to do particle image velocimetry is you need a camera and you need a light source. And so oftentimes we would use a laser, which is fairly high tech. And what we can do with a laser is we can make it into a light sheet, and we can cut through the flow and take a picture of just some slice out of the flow. This is below, this is a mile under the surface of the ocean. And I think there's lots of precedents for working with images that happen to be acquired for some other purpose, but from which you can get useful flow information. Like I've run PIV algorithms on flocks of birds and things like that. I'm a bit of a geek that way. So you can do all kinds of fun stuff with this. And the important thing is there has to be something in the picture that you can see that moves from frame to frame to frame. Question back there?
Speaking of moving, does this technology or this ability translate into measuring what's on the surface then and try to predict where it's going?
Yeah, that's a really good question. So people use codes like this to measure how clouds move, and they call this remote sensing. So there's satellites that orbit the Earth and take pictures of the clouds, and usually you don't use particle image velocimetry for clouds, but there's a related technique called optical flow that if you can see the same kind of information, a sequence of snapshots, you can run an optical flow algorithm on this collection of snapshots and back out the velocity, how the cloud moved between the pictures. So you're right. I don't know that anybody's done that with the oil slicks. And I don't know that it needs to be done, but it could be done. It's a good observation.